So we are still in this lecture 11.5 on Bode plots. And we want to take these building blocks, remember that we were introducing at the end last time, and use them to reconstruct. Oh man, we got the clicking. Can't do the clicking. Thanks. And we've got these building block Bode plots from transfer functions of first and second order systems that we want to use to construct higher order system Bode plot sketches. Remember, we care about the sketches not because we don't have computers. It's not why we care about sketches. We care about sketches because we want to be able to understand how these transfer functions, these first and second order building block transfer functions, affect the Bode plot, because that's essentially governing the frequency response of the system, which is very important when we're designing systems to have a certain frequency response. So for instance, if we want a system to have very little response to certain frequencies, we would like there to be a dip, say, in the magnitude of the frequency response function at those frequencies. Or maybe you want to filter out high frequencies. So you want to have high frequency response function magnitude be very small. So understanding how these first and second order transfer functions contribute to a Bode plot of a higher order system is going to help us do that. And for a low order system, for a first or second order system, we don't even really have to go back to building blocks because we already know it's just one of the building blocks. So that's kind of where we're at. So today we're going to finish up our building blocks, and then we're going to review for just a moment how to reason through this idea that we can break these Bode plots down into these building blocks and sum them up. Okay, so that's what we'll do, and then we're going to do an example. So it's going to be great. It'll be a great time. Complex conjugate pole pairs and zero pairs. So we did roots. So we did real root, real pole, real zero Bode plots. So those were the not those ones. These ones, right? Break frequency happens, and then we got this 20 dB per decade decrease in the magnitude, and then in the phase we got this go back a decade, go forward a decade, draw a straight line, and that's approximately what the phase shift is for a first order real root, real pole, or real zero. And now we're going to do this complex conjugate pole pairs and zero pairs discussion. So we're going to just look at them, and we're just going to interpret them. So 11.5 is the figure. So let's first consider a complex conjugate pole pair, which has a transfer function like this. So when you're going to use these building blocks, you have to express that part of your transfer function in exactly this form. Okay? And it's very important. We have to do that. We can't forget that part. That's the part that is very hard to remember sometimes. So you got to remember this part. You got to make it look just like that. That means you have to have whatever factor shows up in the numerator has to show up in that spot in the denominator. Okay? So that's important. We got like this omega n squared there has to be an omega n squared in the denominator and in the numerator. So that has to be done in the way we rearrange it. So I'm going to do this in the example. We're going to see an example of having to do that. So don't worry, that's coming. Now, we have let's look at the magnitudes first. So for the magnitude for a complex conjugate pole pair, we start off our sketch as being 0 dB. We go up, and there's this break frequency, right? And this break frequency, after that, it has this slope of negative, instead of 20 dB per decade, now we have a slope of negative 40 dB per decade. And with the single pole, with a single real pole, we had a slope of negative 20 dB per decade after the break frequency. Now, what does this break frequency correspond to in terms of actual frequency? Notice that we're at 10 to the 0 in normalized angular frequency here on the Bode plot. Normalized angular frequency being omega, the actual frequency, over the natural frequency. And it happens when we are at 10 to the 0, in other words, 1. And that tells us that our break frequency is just the natural frequency. Okay, so there's our break frequency. Very important. So notice that for different damping ratios, we deviate from this straight line approximation relatively significantly at or near this break frequency, right? Now, the way that we're going to handle this in terms of sketching is that we're going to refer back to this plot, and we're going to say, okay, say I have a damping ratio, I compute it, it's 0.23, okay? It's not one of my damping ratios here, but it's in between 0.1 and 0.3. So when I go to refine my sketch from the straight line, I will go between the blue line and the burnt orange line, and I'll say, okay, the actual plot looks something like that. And that'll be my refined sketch. Okay? Great. So that's our magnitude of the second order complex conjugate pole pair. Okay? Not terrible. You do have to do a little bit more like meh, and one of the ways to decide how big to make the bump is to say, oh, okay, well, the say 0.1 damping ratio peak happened at say 15 dB, and the 0.3 happened at say 5 dB. So we'll make the one in between be around 10 dB, and that's going to be our approximation. Okay, it's a little bit tough to do this perfectly, and the sketch is never going to look perfect with this, because you're really just like looking for like a shape on a line and hit a couple points. It's kind of what you're doing. So don't worry too much about it. This is the type of thing that it's good to be, take a little bit of care when you're drawing it, but it's not something that is worth obsessing over, because we're going for qualitative features here. That's mainly what we're after with the sketch, qualitative features, not quantitative. We're not going to read some value off the graph and be like, that's how much the magnitude is at that frequency. If we're going to get that precise, we'll just use a computer to plot it and find the exact value, or a good approximation. So great. So then the phase, the straight line approximation that we make for the phase is that we start off at 0 phase, and then at the break frequency we just draw, this is sort of like a construction line, and draw a straight line down to negative 180, and then we flatline it there. Okay? Not a great approximation unless zeta is very, very small. If zeta is very, very small, then we have a pretty good approximation by just this step. Yes?
So zeta is the damping ratio?
That's right. Mm-hmm.
So could you use this, like what kind of real world situation would you use these?
That's a good question. So do you remember in the mechatronics lab in ME316 when you guys did the RLC circuit lab, when you put in a sinusoid to the RLC circuit and you measured the amplitude and phase shift of the output amplitude, and you plotted the amplitude ratio, the output amplitude over the input amplitude, and then also the phase shift for each of these? And when you went through, there was some frequency that you hit where the output amplitude went up a lot. And that was your natural frequency, approximately. And what you were hitting there is you were hitting this part of a second order complex conjugate pole pair Bode plot. And so what you guys actually plotted was this, the output amplitude over the input amplitude. Remember the input amplitude in all our derivations was A. The output amplitude was A times the magnitude of the frequency response function. And so if you want to know what the ratio of them is, A's cancel, and you just left with the magnitude of the frequency response function. So that's what we're looking at. We're looking at the magnitude of the frequency response function, which is the output amplitude over the input amplitude. And when we get close to the natural frequency, the output amplitude is much greater than the input amplitude. And that's the type of so that's an oscillatory circuit. So if you drive it at a frequency that's close to the natural frequency, the output amplitude is much greater than the input amplitude. Yeah?
So, like, if you were to put this into a physical system,
Mm-hmm.
that would be the blue line would be like your amount of vibration. So, like, if you have, like, you know, like your car door,
Mm-hmm.
you, like, go over a certain resonance pattern, like in the road,
Mm-hmm.
and then that would be like where the loudest would be, like at that point.
Yeah, so you can think of that as so like there are a lot of parts on cars that when you excite the car at that frequency, it'll start to rattle. Okay, and so if you've got, say, like a loose something in your car and you hit like this frequency with the input, so maybe you're going a speed that like hits the transitions in the road like just at just the right frequency, and it starts to like shake something significantly and it gets loud. That would be an example of this type of system, a sort of resonant second order system. Another example would be when cars drive by my house and they're going a certain speed. I don't know what speed it is, but it rattles the shit out of my door. I just hear this like, and it's like why? But I have like this like metal weather stripping on there, which I would need to replace. But the metal weather stripping, like it just hits some vibration mode. It gets excited and it just rattles at that frequency. So that would be close to, say, this frequency for the metal stripping. And then it gets excited. Most cars that drive past, it doesn't even bother it. So we're like, usually like we're out here, there's no rattle, there's no amplitude that's significant enough to make it rattle. And then down here, not, but then right here at that frequency. Another thing is a swing. So if you were to think about a swing, if you push on a swing at a very low frequency, so like you push it forward, you pull it back, you push it forward, you pull it back, you're just going to move back and forth at the same amplitude you're being pushed, right? But if you increase that frequency to the right frequency for the natural, so to say like the frequency that it would oscillate at if you just let it go, then you get this increase in amplitude every time, right? If you start to do too fast, it's not something that you've probably ever done because it's never seemed to make sense to do it. But if you were like trying to like push really, really rapidly on somebody on a swing, like they wouldn't go anywhere. Like, it would just be sitting there. So it doesn't. It's not a perfect second order system, but it's one way of thinking about this sort of second order system where we have this increase in output amplitude at a given frequency or near a certain frequency, and then other frequencies not as much.
So the Bode plot is the top one, right?
Yeah, well, it's both. So the Bode plot is actually the magnitude plot and the phase plot together. It's just like, we call it the Bode plot because that's just the tradition. So, yeah.
So like I can visualize the top one, but like what it's doing.
Yeah.
I don't really understand what the plot is.
So and actually we finished the top one, so now we can talk about the bottom one. So the phase it's the difference in the phase between a sinusoid that was going in, say that sinusoid, and a sinusoid that is coming out, which I'll try to draw at a different amplitude too. So the phase shift is the peak-to-peak fraction of the period. So that's the phase shift, and that's our phase of the frequency response function at whatever frequency these sinusoids are at. So omega naught being whatever the frequency is that these are oscillating at. So this is the phase plot says that at different frequencies, this phase shift changes. So at low frequencies, the input and the output sinusoids have like the same phase pretty much. They don't have any offset between them. But as you increase the frequency of the excitation, the input frequency, the output's going to start lagging behind, okay? And it ends up lagging by 180 degrees. So this phase shift increases to 180 degrees when you start to go at higher and higher frequencies.
So with that like gap that you drew, would be like that direction on the graph. Yeah.
The gap that I drew would be one data point on this graph.
Yeah, but it's going the other direction. Like so the gap
Oh.
that you drew was vertical and the gap would be horizontal.
Yeah, so we're plotting the gap here on the vertical axis. Yes.
So you could like look at your x-axis and see your frequency and then
Right.
know that.
So you would say, okay, what is the frequency of that sinusoid? Well, it's at, say, 3 times 10 to the minus 1, and we have negative 30 degrees of phase would be the difference between these two sinusoids. So that's the way we can interpret it. So for a given frequency, this is the phase shift. It's the phase offset.
So it'd be like a 30-degree delay then.
Yeah, exactly. Okay, so very good. So we've got this straight line, and then clearly it very much depends on what the damping ratio is in terms of which of these curves we've got. And this is like one of the hardest ones this is probably the hardest one to draw, to sketch. So what we do is we say, okay, once again, maybe we have a zeta of 0.23 or something. It's in between the blue and the burnt orange. We just do our best to draw a curve that's between those. And it's harder when you don't have the other ones already on there as guidelines. So and we'll do an example of this. It's a little bit tricky, but we do our best to try to round it properly. I'm very lenient on this part because it's actually quite difficult to do it well. And it's tedious, and I'm not really like trying to get you guys to do this great sketch. It doesn't really matter that much. Really, it's the qualitative thing. It's going to shift by 180 degrees over a couple decades in a sort of S-curve shape. That's the main bit. So, and then for the zero complex conjugate zero pair, which is more rare, very much more rare than the complex conjugate pole pair. But when that does happen, we have essentially a mirror image of the pole pair situation, and these are the different curves that you get. Once again, starting out at 0 dB to the break frequency, and then going at, instead of negative 40 dB per decade, going at positive 40 dB per decade, and the phase going from 0 to positive 180 instead of 0 to negative 180. So that's the difference. And it has the same break frequency, again, the natural frequency. So let's go ahead and let's review quickly. Actually, I'm going to just try moving to this section here, because I try to explain it in here. We might have to review a little bit if we don't remember some of the arguments, but I think we'll do okay. So we'll try. So we can use MATLAB's Bode command to create Bode plots from LTI system models. However, we must understand how these plots relate to their transfer functions. In this section, we learn to sketch Bode plots in order to deepen our intuition of this relationship. So this is where that specific discussion really gets into the details. So let a transfer function be the product of these sub-transfer functions. And if we take the magnitude of a product of sub-transfer functions, it's just the product of the magnitudes. Okay? Good old-fashioned magnitude property. And if we take the phase of a transfer function with a bunch of sub-transfer functions, what we do is we sum the phases. Now, this is nice because if you have a bunch of phase plots of your sub-transfer functions, remember our building blocks, then all you need to do to combine them up into the complete transfer function sketch is to just sum them. And summing things graphically is pretty easy, right? If you've got 4 graphs and you want to know what the sum of them is you just add up the 4 values at each x-axis value, right? So say you had 3 plots. One was at height 4, one was at height 3, one was at height 0, one was at height -2. You just have to sum those up to get 5, right? And so if you summed all those, you would get this as your, or whatever, this. I didn't really do it to scale anyway. But you would get that as your sum, right? You just add up the values. That's the idea. It's not super hard to add graphs together. Been doing it for a while. So this, like the phase thing, is already done. We break it up into these sub-transfer functions, into those building block transfer functions. We know what those Bode plots look like. We sketch them with straight lines, and then we just sum them. Okay, so the phase one is like done already. The magnitude one, not so great though, because then graphically multiplying is not as easy to do. Graphically multiplying, meh, not so awesome. So we do this nice, this is part of why we express the magnitude in dB, because it's a logarithmic quantity. So a logarithm takes the product and turns it into a sum, okay? And now we've got a sum of dB magnitudes, which is how each of these individual building blocks was plotted above as a dB magnitude, right? And we've got a sum of phases. So now all we have to do is sketch the building blocks individually and then sum them for each, the magnitude and the phase. So that's our general approach. That's what we're going to do when we try to sketch our Bode plots. Great. So let's do an example. Given the transfer function below, answer the following questions and imperatives. And this is adopted from an exam question. Okay, so for what it's worth, red flashing light, ding, 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 right? Okay, definitely should be paying attention to this example. So it's a little bit, I stretched it a little further because, like, I asked a question about MATLAB and whatever. Like, you can't do that on the exam. I know, it's fine. But let's go through this. So given this transfer function, the first part is to sketch a Bode plot in figure 11.6. What is 11.6? 11.6 is a blank Bode plot, right? Wonder if something like this will show up on an exam. That would be crazy, wouldn't it, if that showed up? Okay. So we've got this blank Bode plot, and we need to fill it in. So we've got a transfer function that is third order. It's got a 0 It's got a big constant out front, and let's go ahead and do it. So part A, so sketching the Bode plot, we want to begin by breaking it down into components, right? Breaking into building blocks. And I kind of do this in two steps. What I first do is I want to get it into approximately the right form where I'm not worried about the constants so much. I'm just worried about the overall form of like, is this a real pole? Is this factor stuff out? All that. But if I'm gonna wait to deal with the constants until the next step, because dealing with the constants in the same step is pretty hard to do. So let's go ahead and leave the constant alone to start. So that constant was like 200,000, right? I'm going to put 200K because I don't want to write all the zeros. It's harder to see. So 200K. And we have, that's a constant. That's one of our building blocks is a constant, right? So we'll just leave that by itself. Times another one of our building blocks is a real zero, right? So s plus 1, that's a real zero up there. I'm going to just, because that zero is what? What's the zero corresponding to that term? -1. That's real, and it's a zero. It's a real zero. Yeah. You all right?
Yep.
Well,
I think I just broke my kneecap.
ouch.
We're good though.
That sucks. You know, I always say this stuff it's very exciting. Just like, be safe though with it. Yeah, I know it's really good stuff, but yeah, try to be safe. Try to be safe. Okay, so all right. So we've got our real zero, and now we have 3 poles, right? And so there's a question here. So it's either going to be that the poles are all 3 real poles, or we're going to have 1 real pole and a complex conjugate pair. You can't have 2 complex conjugate pairs because there's only 3 of them. So you can't have 2 pairs out of 3. That's just cards 101. Okay? You can't. That's how it works. I don't know. I should bring candy and throw it again. So we want to find out if we have 3 real poles or if we have 1 real pole and a complex conjugate pair. So the easiest way to do it is just to find what the poles are.
Factor the polynomial?
Yeah, so you could factor the polynomial. So that's one way to go with it to find the poles. And so sort of like sidebar, what are the poles? I'm going to recommend, so if I'm going to have you guys compute poles, construct the Bode plot, you're going to have numerical, it's going to be a numerical polynomial, right? So finding the roots of a numerical polynomial, whenever the denominator is equal to 0, the roots of that are the poles. So we have many ways, including your calculators, right? Your calculators can find the zero, or they would call them zeros of functions, right? Zeros of polynomials. So that's one way to go. If you can see a factorization, go for it. I mean, if you want to do numerical root finder with higher order ones is required. Lower order ones, technically, there are formulas. If it's quadratic, you probably don't need your calculator. But yeah. So what are the poles? In this case, the poles come out to be, I don't know what I used, but I used some sort of numerical, probably MATLAB. And and they came out to be -10, maybe. -10. There's a real one. And then a complex conjugate pair. So -50 plus J 86.6. I think that's a rounding. I don't recall for sure. And then plus, and then -50 minus J 86.6. So this is a pole pair, right? This is a complex conjugate pole pair. Complex conjugate pole pair. So that's that building block. And this is just a real pole, right? Great. So let's go ahead and just write them out then as a product. So the real pole, 1 over, so this pole happens at -10, so S plus 10, right? And we take the product of that with 1 over, 1 over, and now we need to know what's left, right, after you factor out that S plus 10. How do you factor out, just by hand, if you wanted to, S plus 10 from this cubic polynomial? This is just a little sidebar. You would write that polynomial, S cubed, just long division, right? Plus 110 S squared. It's been a minute probably since you guys have done this. 11,000 S plus, oh, didn't give myself room, plus 100,000, is that right? Yeah. And you put it in long division with whatever you're factoring out, so S plus 10 in this case. And you go through and you do your long division. Whatever ends up here is what's left. Okay? And that ends up being S squared plus 100S plus 100 squared. So plus 10,000. Great. Now we're getting close, right? We've got pretty much the building blocks that we need, but we need to check very closely what the form of each of them is to get essentially the overall scaling factor correct. That's our biggest step to do that's left. And when we do this step, what I like to do is leave the constant out front alone to start, because this constant's gonna absorb the factors we need to put in and pull out from these other guys. Okay, so leave your 200,000 out there for a minute. Let's keep track of what needs to be pulled into it before we write it down. So first of all, this S plus 1, is this in the right form already? It's a real 0. So a real 0 has this transfer function in order to have this Bode plot, which is what we want. So is that one in this form of tau S plus 1? So what we have is S plus 1.
Well, tau is just 1.
So tau is just 1. Yeah, so it's good, right? S plus 1, and we can call this tau 1 equals 1. Okay? Good. And then we can do this next term. So 1 over S plus 10, a real pole. Let's go back and look at the real pole. And the real pole has transfer function 1 over tau S plus 1. We don't have a plus 1, we have a plus 10, right? So we have to divide the denominator by 10 to get to the form we want. So we need to do 1 over 1/10 s plus 1. And we identify that tau 2, we'll call it, is equal to 1 over 10. Good. Now, if we divide the denominator by 10, we're going to have to do something with, or if we factor out 10 from the denominator, I guess, would be the way to put it. If we factor out 10 from the denominator, we're going to have to pay for that in this constant out front, right? And so we factor out a 10, we're going to cancel one of the zeros from this 200,000. So we're down to 20,000 now. Cool. But we're not going to write it because we've still got one more term. And this one, we have a complex conjugate pair, pole pair, right? So that's this transfer function. And this one has, this looks good. The denominator is a second order polynomial and whatever. But we don't have this numerator here. It's just a 1, right? Omega n squared. It needs to match with the last term. It needs to match with the s to the 0 term in the denominator. Now, we can make it happen, right? So 100 squared should be in the numerator because that's where it is in the denominator. So we've got 100 squared in the numerator divided by s squared plus 100s plus 100 squared. So that looks good. That's in the right form. But we multiplied the numerator by 100 squared. So you got to divide somewhere by 100 squared. So we do that also off this, what is now 20,000. So we've got 4 zeros, or 4 factors of 10 from this term, 1 factor of 10 from this term, so 5 factors of 10 total that cancel this 200,000, right? And 200,000 has 5 factors of 10, right? It has 5 zeros. So we just left with a 2 here. And if you ever like, did I do that right? Just try multiplying it back out. See how it works. Does it come out to the same thing? Can you put it back in the form that it was in before? Can I pull out this 100,000, multiply 10 through here, and then get back to my original value? And then that's a good check. So it's an easy place to mess up. Now let's identify from this last one a couple parameters. First off, we see that omega n is 100, right? Just from the form, the standard form, that's what omega n is equal to. So there's our omega n squared, so 100 is our omega n. And then this term, 2 zeta omega n, has to equal whatever is there in our function. So 2 zeta omega n has to equal 100. 2 zeta omega n has to equal 100, where this 100 came from there, okay? Which tells us we know omega n is 100, 100 and 100 cancel, and zeta is equal to 0.5. Okay. So now we have all our building blocks, and we're ready to start to do the graph, right? So let's do it. Let's do it right. So the magnitude plot, we have I'll start out with green, say. The first term, actually I'm going to copy it down here. It's going to be a little bit of a challenge to scroll back and forth, so okay, so that's what we're going to be plotting. Remember, this needs to be in dB, so the constant's super easy. It's just a straight line across, but needs to be in dB. So converting 2 into dB comes out to be about 6 dB. So say there. Oh, I'll do I'll do green. So 6 dB. Great. Now we need to do, so this was that one. Now we need to do, so I'll do red. The next term, which is the real 0, s plus 1. So real 0 starts off at 0 dB up to its break frequency. So we got to figure out what its break frequency is. So omega break 1 is going to equal, it's a real 0, so it is equal to 1 over tau 1, which is just equal to 1 over 1, or just 1. Great. So that one is 0 up to the break frequency of 1, and then it goes at positive 20 dB per decade, so positive 20 dB per decade. And it keeps going, but leaves the graph there. Leaves the bounds. So then let's do blue. And we've got this term here, which is the real 0, or real pole, I should say. It has a break frequency of being 1 over tau 2, which is 1 over 1/10, or 10 radians per second. 10 is here, so we've got 0 up to 10, and then we've got a negative 20 dB per decade slope. Now, we should do a little rounding of like 3 dB here, right? And red. It's not too bad to do that. We could do a little bit more drastically. Yeah. So that's our poor rounding job. Okay, and now we are to the last term. And the last term is, I'll do it in purple. The last term is 0, so it's a second order pole pair. So it's 0 up to, the straight line goes to the break frequency, which the natural frequency is the break frequency for a second order system, and that is 100 in this case. And then we have a slope of negative 40 dB per decade thereafter. So now let's sum them. So we've got them. Oh, well, we've got to do a rounding, right? We said zeta was 0.5. If zeta is 0.5, we go back here and we say, zeta being 0.5 gave us a pretty much no hump, maybe just like a little bit of hump for the second order system. So maybe we do like something like that. All right. So now we sum them graphically. I'll do this nice baby blue. 0 plus 6 is 6. So it's just like 6 all the way up till we start to increase here with the 0. And then we start having this nice straight line following that 0 until we get to where the real pole starts coming in, and then we actually flatline, right? Because negative 20 dB per decade and 20 dB per decade cancel each other out. We're flat, and then we go through this hump here. Is maybe not quite that drastic. And then we come out here, we're going to be at negative 40 dB per decade slope, something like that. So that's our composite sketch. Okay? I forgot to do purple highlight here. Yeah.
How'd you come up with the slope part?
Yeah, so that's just based on these graphs back here. So the at high frequency for a complex conjugate pole pair, we have a slope of negative 40 dB per decade. With a complex conjugate zero pair, we have positive 40 dB per decade. With a real polar zero at the origin or not at the origin, we have a negative 20 dB per decade or positive 20 dB per decade slope. So that's how I knew what the slopes were. And then when you have slopes summing together, they can cancel each other out essentially. So you have negative 20 and positive 20, and you get 0 from that. So that's how we did the slopes.
So how did you decide that the S+1 was a positive? What is it? Is this the real?
Because it is a real 0. So since it's a real 0, S+1, if you go back up to the real 0, which is this one, then it has a positive 20 dB per decade slope. Yeah. Great. So let's do the phase one really quickly, and we've just got a couple minutes, maybe, if extra time here. I don't see anybody waiting for us. So let's do the same thing. Let's say for the constant. The constant has 0 phase shift. Okay, the 0th order system is 0 phase shift. Bam. So that one's easy. If we go to the real 0, which has the red, then we have a positive 90 degree phase shift that starts happening 1 decade below the break frequency. The break frequency for that was 1, right? So 1 decade before is going to be right away for us. And it goes from 0 to positive 90 in 2 decades, going through 45 degrees at the break frequency. And thereafter, it'll be a flat line. Okay. And then we've got blue. And blue was the real pole. And the real pole has a break frequency of 10 to the 1. So it starts off flatline phase. A decade before the break frequency, it starts to go down, and it goes through negative 45 at the break frequency, and it ends up at negative 90 where it flatlines. Okay. Finally, we've got this second order complex conjugate pole pair, which we're doing in purple. And that one has a 0 phase up to, the straight line is up to the break frequency. So we'll just go up to the break frequency. We'll draw this sort of like sketch, maybe thin line down to negative 180. And then it's flat after that. But we're actually going to have zeta of 0.5 gives us really much more of like an S curve, right? So over 2 decades, it does pretty much a complete S curve to negative 180. So it's a little bit hard to draw this, but I would say it looks something like this. It's not perfect, but it's okay. That was a little bit better. So now we just need to sum them. So now we've got our baby blue for the sum, and it starts off going up, it's just like this, and then it's like, okay, now I'm gonna flatline, but so I'm gonna flatline, and then what happens here is this guy stops contributing because it just goes to flat. So now we're going to have to start going down. We have to drop essentially 90 degrees in this whole time down to negative 180. So if you sum them up at the very last point here, we have 90 minus 180. So you have to get down to negative 180. So somehow we have to kind of go in like somewhat of an S curve down to negative 180. Something like that. It's not perfect. It's probably more like this, where it follows the other S curve at the last bit.
This is kind of the average between all the lines.
It's the sum. It's not the average, it's the sum. It's very specifically the sum. Yeah. Okay. I kept you guys very late, so I feel like I should let go. But if you have any questions, stay around afterwards or ask now.
So, given these, like, the negative 20 and 20, like what they are on the exam, or do we bring that in?
I mean, they should be in your notes.
Oh, yeah,
Yep. That's so yeah. So you can have them. You should have them there. Yeah. Yeah, don't forget the exam is open notes, but closed book. So as you study, keep that in mind.